Electrical impedance spectroscopy is a relevant research field which has multiple uses in biotechnology and medicine. Biospectrum aims to design and optimize a microfluidic prototype of a 4-channel electrical impedance measurement system up to 2 GHz for biological suspensions. Our device consists on 4 chambers where the biological suspension can be confined. The planar electrodes work as sensors which allows to measure the suspension impedance while perfusion of the medium feeds the cells for long-term experiments. Modeling and simulation tools are of great relevance to this field. Using ANSYS packages for simulation, Biospectrum aims to define and optimize the geometry and dimensions of the microchannels and microchambers. Define and optimize the geometry and dimensions of the interdigitated planar electrodes. Define a standard protocol of use for the device. The CFD simulation has 2 main objectives. The first one is to analyze how the shape of the geometry impacts pressure, velocity, and wall shear stress profiles. The second objective is to optimize the back pressure channel's length in order to obtain equal flows in each chamber. The first step of the simulation is to analyze the original geometry and determine the initial values of the flows inside each chamber, along the maximum pressure, velocity, and wall shear stress. The optimization was done using this data as a milestone of the experiment design. A response surface was created using ANSYS Response Surface Optimization package, characterizing the variation of the output parameters in function of the back pressure channel length. After a mathematical optimization process, the final geometry was obtained. This geometry guarantees equal flow rate throughout the chambers with a maximum difference of 2% with respect target flow. HFSS was used to verify the functionality of the coplanar capacitors at the expected frequency of operation. After analyzing the results of the original geometry, the decision was taken to change the design in order to keep more consistent characteristics throughout all 4 sensors. The simulation of the S parameters shows that the device presents little reflection for the range from 0 to 2 GHz when matched to a 50 ohm impedance. Also, it's evident that the parameters change dramatically when changing the medium of the chamber. Here, the impedance magnitude of the devices changes also when changing the medium. Finally, an animation of the electric field distribution for the structure is shown. Also, an animation of the field is shown in a transversal plane of the chamber. The results obtained using the HFSS have proven to be crucial in the development of the device and have been highly influential in the design decisions taken in the project. Protocol of use. The use of the microfluidic device has 4 main steps. First, the infusion is carried out. A flow of biological suspension is added to the inlet of the main channel. By applying the appropriate pressure, the suspension will enter and load each microchamber. Once the microchambers are filled, the infusion is stopped. The second step is the perfusion. A continuous flow of culture medium is introduced in a perfusion inlet in order to allow long-term impedance measurement. Now, the measurement of impedance can be made.